I'm Jerome, and I'm going to talk about alternatives to power law, and especially we're going to look at fairness. So let's start. What is fairness? So let's say that we all are going to eat a cake together. Then we're going to cut the cake in pieces in such a way that everyone gets a fair share of the cake. So we're going to try to make each piece the same size, and then we are all going to be happy, and that will be pretty fair. But now, of course, not everything in life is so fair. So, for instance, sometimes you have the situation that 1% of the cats own 99% of the catnip. Yeah, and actually, this is not only a joke, but this is based on real history, where something which is called the Pareto Principle, and this is from the economist Wilfredo Pareto, who noticed in Italy in the 1910s that 20% of the people owned 80% of the land. Yeah, and of course you can also take this phrase and turn it around and say that 80% of the poorest people own only 20% of the land. So what would be the equivalent now on the web of owning land? Yeah, so if we are on the web, we're going to be on social networks, and in these social networks, we're going to have, for instance, on Twitter, we all have followers. So we have some number of followers, and usually, for most of us, that's some pretty small number if we put it into perspective with well-known people who can have up to millions of followers. And actually, if you look at a larger percentage of the people, we're going to see that most people have a small number of followers, and only very few people have a very large number of followers. And that, of course, is unfair. And we can do this analysis also for many other sites on the web. So for instance, if you go to Last.fm, where people are listening to music from different bands, then the situation there is that 9% of all bands get played 91% of the time. And you can do that for lots of other sites. So for instance, this joke with the cats actually was not so far-fetched, because if you go to catster.com, where people can register their cats and add some friend to them, then you're going to see that 20% of all cats receive 80% of all cat friendships. And if you look at Twitter now, you're going to see that actually 36% of all Twitter users receive 64% of all follows. So actually Twitter is more fair than other sites on the web. And now, of course, we're going to analyze that in a little bit more mathematical way. And all these examples that I just gave are actually networks. So if you look at a social network, the number of friends you have is actually the degree of you in that network. Or for instance, if you look at Last.fm, where people are listening to bands, then each band is a node in the bipartite network, and the number of times a band has been listened to is just the degree of that node. So we're now looking at a degree distribution, and the standard thing to do for this degree distribution, so maybe I should say what this shows. So in this degree distribution, we have on the x-axis the number of friends that you can have on the web. And the y-axis represents the number of nodes that have exactly this number of friends. So what this means is that we have here only very, very few people having a lot of friends, and most people have not many friends. And the standard thing to do now is something which is done very often, and that's to model that distribution as a power law distribution. So we say that the number of people having exactly n friends is proportional to n to the minus gamma, where gamma is some number. So we just heard some numbers for that before, which would be between 2 and 3. And in this case here we get gamma equal to 1.7. So now let's look at a few more degree distributions. And if we do that, we're seeing that actually not all degree distributions are power laws. So some are power laws, but other are not. but nonetheless, they more or less look a little bit like it. So what people do very often is just estimating the best value of the exponent gamma, which fits that curve. And there are actually several ways to do that, and some are not so statistically founded and other more so. And now we're just going to do that and use these numbers. And what we want to do now is to compare these networks and see which networks have more or less fairness based on these numbers. So as an example, let's take the Flickr social network and the Dig reply network. So that's on the website Dig, who receives how many replies in the discussions. And what we see here is that on Flickr, we got an exponent of about 1.6, and on Dig, we got an exponent which is higher, which is 1.9. So there we would think that on Dig, there are less people receiving a lot of replies and comparatively more people receiving very few replies. So now the question is, which of these two represents a fairer distribution? And now to measure fairness, we're going to use another very famous way, another very famous plot, which is the Lorentz curve. Some people also call it the L curve. And this is based on the statistics that you already saw. So for instance, in that curve, we have a situation that 75% of the poorest people own 25% of things. So that gives us 1 point here on the plot, which is this point. And of course, we can also ask, if we take the 80% of the poorest people, how many percent of things do they own? And then we're going to get a number that's a little bit more than 25%. And if we do that for all numbers, we get this blue curve, and that is the Lorentz curve. And now if we imagine that we got a completely fair distribution, then we would have, for instance, 25% of the poorest people owning 25% of things, and 30% of the poorest people owning 30% of things. So the result would be a curve that just follows this main diagonal here. And in real networks, of course, we don't have that. We have some curve that goes below that. And so to measure the unfairness or the inequality of the distribution, we just look at the area between these two curves, so between the curve and the main diagonal, and this is what's called the Gini coefficient. So in that example here, we got a Gini coefficient of 64%. And now if we go back to our two networks from Flickr and Dig, we see that Flickr, which has had a lower value of the exponent gamma, has a higher Gini coefficient. And Dig, which had a higher value of gamma, has a lower value of the Gini coefficient. So what does that mean? We said that the Gini coefficient, if it is low, then we have a fair distribution. If it is high, then we have an unfair distribution. So that means that for Flickr, we have a more unfair distribution. But Flickr had a lower value of gamma. So the result here is, if gamma is high, we got a fairer distribution, and if gamma is low, we got an unfair distribution. And actually, that is a very surprising result, because if you think about it, if this gamma is high, that means that the slope of the curve in the power law distribution is high. So you would think that there are just very few nodes having a large degree and much more nodes having a small degree. But still, if gamma is very high, the Gini coefficient gets smaller. So how can that be? So maybe now some of you might think that this is a result of the fact that some of these degree distributions are not actual power laws, because actually they are not perfect power laws. So let's just look at what happens if we take a perfect power law and measure the Gini coefficient for it. So that's just what we did here for varying values of gamma. And the result is that when gamma is high, the Lorentz curve gets nearer to the diagonal, which means that the Gini coefficient is smaller. So we get exactly the same effect as with the real networks. So again, we see that a high value of gamma means fair distribution. So that's one result of the talk. And now I'm going to switch to the second part of the talk, in which we're not going to use a method from economics, but from physics. So, and in physics, physicists usually look at matter, which can come in different forms, and one of these forms is a gas. And physicists like to put a gas into a container. So the container, that's what we draw here as a rectangle, and the gas actually is made out of molecules. And the molecules, these are the little dots here. And if you put a gas in a container, the molecules are going to be all around the place in the container, more or less equally distributed. But of course, the molecules, they are not stationary, but they are moving around. So it could very well be that at a certain point, the container would look like this, so that all molecules go on one side of the container. But actually, this is really improbable. And this is so improbable that there is a law in physics which is called the second law of thermodynamics, which says that if we look at real systems, this is practically impossible. So if we have a system which is in this state here, it may very well go into this state, but if you have a system which is in this first state here on the top, it will not go back to this state. So that's what's called the entropy, and entropy is just a number which measures the state of a physical system, and if entropy is low, which is the case here in the second example, then it can get higher, and the entropy is high, for instance, in this first case. And what the second law of thermodynamics states is that the entropy will not get lower again. So now, how can we use that to measure the fairness of a distribution in a network? Well, now imagine that the molecules are just the follows that are distributed over all the people on Twitter. So each one of these little dots gets placed somewhere in the followers list of the people on Twitter. So you have some people like Beyonce, which get a lot of followers, and then other people who get not so many followers. So actually what we see is that the entropy is not maximal, but it's not minimal either. So not everyone only follows Beyonce, yeah? Now what we can do is just look at some real networks from the web and just look at their actual entropy. So that's what's on this plot. So on this plot, each code of 2 letters here, for instance, this one is one network, and we just place it on a point determined by its size, which is number of nodes in the network, and the entropy on the y-axis. And what we see here is that when we draw the plot using a logarithmic scale on the x-axis, we actually get a very high positive correlation between the size of the network, between the logarithm of the size of the network and the entropy. And why is that the case? Well, now let's imagine that everyone on Twitter gets the same amount of followers. Then the entropy, if we just plug that into the definition, equals simply the logarithm of the number of people on Twitter. And so that means that the actual entropy follows that number, but is not exactly that high. So what we can do is just divide the entropy of a network by this maximal entropy, which is the logarithm of the size of the network. And this plot is exactly the same plot as before, only that we use the normalized entropy instead of the entropy. And what we can see here, that all values indeed are less than 1. And if we look, for instance, at the top of the plot here, this network, which is the code RO, that's a road network of California, and that network has a very high entropy, which is almost maximal, so for what it could be. And that's pretty logical because so this road network consists of intersections connected by streets or roads. And of course, there are no intersections with thousands of roads leading to it. So that means that the distribution is pretty equal. And if we go down the plot and look at these plots here, so all the plots that are in pink here are actually from the different language Wikipedias as the distributions of the number of times that pages have been edited. So that just means that some pages get edited a lot and some pages just a very few times. So that pretty much makes sense. And now what we can finally do is just say, okay, let's compare the Gini coefficient of all these networks with the normalized entropy value. And that's a plot here, and indeed, what we observe is that if the Gini coefficient is high, so that means that the distribution is pretty much unfair, then actually we get a lower value of the normalized entropy. And this is, of course, what we would expect. And To finish the talks, on the last slide, I'm just going to show you a comparison of the three methods. So first method, using the polar exponent to measure the fairness, then the Gini coefficient, and then the normalized entropy. So first, let's look at the generality of the measures. So to what kind of networks can the measure be applied? And for the Power law, as we said, the measure can actually only be applied when we have a real power law. And of course, we can also apply it when you don't have a power law, but then it's not so clear what the meaning of that is. So that's a drawback of the polar exponent. Then we can, of course, look at the interpretation. So what's the justification for using that measure? So as we said, Gini coefficient, that's from economy. The normalized entropy, that's from physics. And for the power law, well, there are a lot of different justifications for it. So there's the original preferential attachment, but also like more recent paper like the paper that we just heard. Then one other thing we can look at is how much time does it take to compute these numbers? And actually, the truth is that computing or estimating the polar exponent is much slower than computing these other values. And finally, the coverage. So what's the coverage? Now, if we, when we looked at the degree distributions, there was the effect that very often for small degrees, the power law was not valid. So basically that means that the power law only describes a part of the distribution. And of course for Gini coefficient and for the entropy, these numbers describe the whole data set. So the conclusion from that talk is if you are doing a power law modeling, then pay attention to what it means and whether you can do it. And if you just want to measure the fairness or the equality of the distribution in a network, then the Gini coefficient and the normalized entropy may well be a good alternative. That's it. Thank you.